All right, so last section we'll look at this week is section 8.5, part 4. Okay, and as I said before, it's basically a good review for everything you need to know for the test on Friday. So we're going to look at vectors in space. Okay, what space means is like 3D space rather than 2D. Yeah, not like outer space. Yeah. All right, so first thing is when we do 3D, it's a little confusing to sketch, so we're not going to do much sketching in 3D. What I'm showing you here is just what the coordinates axes look like in 3D. This is basically where we were before. Okay, picture that as like the bottom. Okay, that's the XY plane. Okay, so everything we've done all week has been what I just shaded in blue. Now, the Z-axis is, imagine that coming up. Like if the table is the XY plane, the Z-axis comes straight up from the table. Okay? Just that's the perspective. And your book mentions a rule you can use to kind of figure out how the X, the Y, and the Z axes all point. And it's called, this is called a right-handed coordinate system. Okay? Because it says if you take your index finger and point that in the direction of the x-axis, okay, take your middle finger and point that in the direction of the positive y-axis, then your thumb on your right hand will automatically point in the direction of the positive z-axis. So if the x-axis was towards you guys and the positive y-axis was towards the door, then the z-axis would be straight up towards the ceiling. Okay? So that kind of gives you a way to figure out which way the x, y, and z-axis would point. Now, if you did it with your left hand and you had the x-axis and the y-axis, your middle finger and index finger pointing the same way, your thumb would point in the opposite direction. So if you use your left hand, the z-axis would be backwards from what we're doing. Okay? So any questions on that? X-axis, y-axis, z-axis. Okay, so it's called a right-handed coordinate system. All right, so first thing we're going to look at is how we can find the distance between points in 2 points in 3D. Okay, how do we find the distance between 2 points in 2D? What formula do we use? The distance formula, which is based off of the Pythagorean theorem. Okay, so every formula I put up today, I'm going to put up the 2D version first, and then I'm going to put up the 3D version. So if you just copy the 3D version, that's all you really need to do everything. But if you want to copy each one separate, you can. All right, so in 2D, your coordinate would have an x value and a y value. Well, in 3D, our 2 points, I'm calling them my first point and second point, not only have an x and a y value, but they also have a z value. So the distance formula in 2D, you do the difference in the x's and square it, plus the difference in the y's and square it. Anybody think we know what we're going to have to add on to that for 3D?
The difference in the z squared?
Yeah, the difference in the z squared. That's the only thing you have to do, and that's pretty much how every formula works today. You just have to add something on to the end to it to make it work in 3D. Okay, so if you copy down the 3D version and you're doing a 2D problem on the test, just go like this. Just don't use the 3D part. Just cross the z's out. Pretend like they're zeros. All right, so let's take a look at those 2 points and see if we can find the distance between them. Okay, I didn't go through the proof of this formula, and we're not really going to go through any proofs of formulas today. We just kind of looked at the pattern in 2D and said, well, that's probably the pattern in 3D. And it is. And the proof of it uses the Pythagorean theorem, except it's the Pythagorean theorem in 3D, not 2D. Okay, so the first thing that I usually do is just set up that entire equation, leaving blanks for everything you're going to plug in. Does everybody have up to P2? So the distance is the square root of, I'm going to subtract two things and square it, subtract two other things and square it, and then plus, subtract two more things and square it. Okay, so now let's just fill in all 6 numbers. Ethan, what would I fill in for my first 2 numbers that I'm going to subtract? Yeah, you're going to plug in 4. That's x2. And then minus -1. You're just got to be careful there because we have minus a minus. So when we do that out, just be careful with arithmetic. Lauren, what would be the next 2 things I'd plug in?
-2 minus 3.
Yep, we got -2 minus 3. And Bria, the last 2 things I would plug in?
5 minus 2.
5 minus 2. Okay, so just do that out, and that's the distance in 3D. So Alex, what's 4 minus -1?
That should be 5, possibly.
Yep, and if you square it?
That would be
25. Good. Fred, what's -2 minus 3? -5, and if you square it?
25.
Still 25 again. And the last one, John, what's 5 minus 2?
3.
Oh, sorry, John, C. 3, and if you square it? 9. Okay. That's it. So the distance between those 2 points is the square root of 59. Just like we always do with roots, if you get something you can reduce, you need to reduce it. If they ask you to round it to a decimal, you just use your calculator. So any question on how to find the distance between 2 points in 3D? Okay, that specifically is the only thing we're not going to do today it's not vector related. It's just 2 points, not 2 vectors. Okay, everything else is going to be vectors. Okay. So, remember, in 2D, okay, if you want to write a vector in unit vector notation, you have a horizontal component times I plus a vertical component times j. Or if you want to talk about it more generally, an x component, an x-axis component, a y-axis component. Okay. Now in 3D, I not only need the x-axis component, the y-axis component, what else do I need? Yep, I need the one that's on the z-axis. So A was the x-axis, B was the y-axis, C is going to be the component on the z-axis, and K is a unit vector. Okay, remember, these are bold, the I, J, and K. I is a unit vector that points 1 unit on the x-axis. J is a unit vector that points 1 unit on the positive y-axis. And K is a unit vector that points 1 unit on the positive z-axis. I can't really say left, right, up, and down anymore, because when you do 3D, it's better to say it the way I just did.
What if you have like a vector that's on the y and z axis, but not on the x axis?
Then you could put a 0 for that component.
Okay.
Yep. So if you just had a vector that was in the yz plane, you would have 0i plus something j plus something k, or minus. Yep. If you want to write it as an algebraic vector, you can use the brackets. The only difference is instead of 2 numbers, you have a comma b comma c with 3 numbers. Okay, so both of these are the same thing, just different ways of writing it. Okay, so A, B, and C, we just went over that. Those are the components of the vector. Okay, if you have a vector that has the initial point at the origin, we had a name for this in 2D. Anybody remember what the name is? A vector with the initial point at the origin. Yep.
Origin vector.
Position vector. Yep. So you already have this in your notes. You already have that. It's just the same name in 2D as it is in 3D. Okay. Any questions on that? Right, so we had a formula in 2D for finding a position vector. Okay, we did this, this was on the last test. In 2D, that's how you find a position vector. You subtract the x components, comma, subtract the y components, and put angle brackets around it. So in order to do that, what they would have given you in the problem is P1 and P2. P1 would be an initial point. P2 would be a terminal point. Right, so you don't have to write down the recall part, because you have that in your notes when we did this already. This is the new part. The difference is when they give you an initial and terminal point, they got to give you a three-dimensional point. So it'll have an x, a y, and a z coordinate, and then an x, y, and z for the terminal point. So how do you think my formula for the position vector is going to change? This one is 2D. What do you think I'm going to have to do to make it 3D? It's kind of the same idea we just did with the distance one.
We do C2 minus C1.
Yeah, on the end of the position vector formula, just put in a z2 minus z1. Okay, so if I was going to put a formula on the reference sheet for the test, this is the one that I would put. And then if there was a problem on the test that was about 2D, I would just cross the z's out and not use them. Okay, pretend like they're zeros. All right, so what I want to try to do is use these 2 points, okay, that we're given to find the position vector with that formula. Okay, this time what we'll do is let's write the answer with the angle brackets first, and then let's also write it with I, J, K. Okay, because you're going to probably see both ways on the test. Okay, so to find the position vector between P1 and P2, can anyone tell me what the x component would be? Priya?
4 minus -1.
Yep, it would be 4 minus -1, which is?
5.
So we get 5. How about the y component? Yep.
6 minus 2, which would be 4.
So 4. And lastly, the z component. Ian?
-1.
-1. 2 minus 3, which is -1. There's your answer written as kind of, we call that the algebraic vector form. How about if I wanted to write it with I, J, and K? How would I write it that way? Yep, Brad?
5i plus 4j minus, just minus k.
It's minus K. Both of those answers are the same thing. If you want to put a 1 in front of the K, you can, but you don't need to. Okay. Questions on how to find a position vector? Because I'm going to ask you this again on the test, even though we already did it in 2D. I'll probably ask you to do one again in 2D, which would be exactly what you just did, but these 2 numbers would be zeros. You wouldn't have them in 2D. So it's a little faster in 2D. And I'll probably ask you to do one in 3D. All right, so next thing we'll look at is the formulas for adding, subtracting, and scaling, and finding the magnitude of a vector in 3D. Okay, we're going to jump right to the formulas. We're not going to do any of it visually like we did in 2D. Okay, you can in 3D. If you have two vectors and you put them together, then you connect where they begin and end, where one of them starts to the other one that stops. You can still do it in 3D, but it's a lot harder to draw it out. So for our purposes, we won't be drawing it. But Ethan, can you just set it? Thanks. All right, so if you want to add these vectors together, in 2D, you would add the x's, the x components, comma, and then add the y components. Now in 3D, you also have to add the z components. Now I put addition and subtraction in the same formula. If you want to write them separate, you could. Okay. But if you want to do v minus w, then you do x1 minus x2, y1 minus y2, z1 minus z2. When you subtract them, does the order matter if you do x1 minus x2 or switch it around? So let's say you add numbers 3 and 4. If you do 3 minus 4 or 4 minus 3, does it make a difference? Yeah. Okay, if you do it backwards, what's going to happen is you'll get the right numbers, but they'll all be negatives. So you'll get just the wrong sign. Okay, with addition, the order doesn't matter, but try to stick with the order that I put right there. Okay, anybody remember what we call this when we multiply a number times a vector?
Scalar.
It's a scalar. Okay, what are the three things that a scalar can do in 2D? And it's the same thing in 3D. Can make a vector shorter. Could make it longer. What kind of number would make a vector shorter? A fraction. Like 1/2, 1/3, 2/3, any fraction less than 1. Numbers bigger than 1 would make it longer. And what's the third thing?
Oh, it can change the direction. Right?
And what kind of number would change the direction?
The negative.
A negative. Okay. So in 2D, I kind of explained it like a distributive property. If you want to scale a vector, you multiply the x component by the number, the y component by the number, and now you have to multiply the z component by the number. Okay, and the last formula has these double bars around the v, and it means the same thing in 3D as it did in 2D. What do those double bars mean? Magnitude. Okay, how do we find the magnitude in 2D? Yeah, so what would we do? Let's pretend that, I'm just going to scroll up and make this a little smaller. Let's pretend this wasn't here. How would you find the magnitude of v in 2D? What would you do?
You'd square x and y and add them together under the square.
Yeah, you'd square the x and the y, add them up, and then take the square root. So it would look something like, go back. All right, I was trying to get rid of the scribbles on the z. I guess I can just go like that. Okay, so there's your formula in 2D. How about, what am I going to add on to that to make it 3D?
Z.
Plus, not
Z squared.
z1 squared.
Same thing.
Correct? So you square the x component, square the y component, square the z component, all separate, and then add them together and take the square root. Okay, so next we'll try some of those. We probably won't do all of them, but maybe we'll do addition or subtraction. We'll do one or the other, and then we'll do a scalar and a magnitude. Okay, does everybody have the formula?
Do we have to find angles for vector that's 3D?
Yep.
How do you-
Exactly the same way you do it in 2D. Well, that'll be the next thing after we talk about the dot product in 3D. And if you ask how do you do the dot product in 3D, exactly the way you do it in 2D. Just one extra step. All right, so let's do V plus W. Okay, so Jacob, if I do V plus W, what would my I component be?
5,
Yep, I get 5I. And Brad, if I'm still adding them, what would be the J component?
-1.
Yep,
J.
so you could put -1J or just -J. And Denver, the K component.
Three.
3. That's it. So if you're going to add them up in 3D, that's all you got to do. Or if you want to write it with the angle bracket, put 5, comma, -1, comma, 3 in those brackets. Okay, so part B, find the magnitude of V. So Nick, can you start to set that up for me, how I would get the magnitude of V?
square root.
Yep, so that's a good start. We're going to start with the square root. You want to keep going? All right.
2 with the square root by 2 to the power 2
Yep, so 2 squared
plus 3 squared
plus 3 squared.
plus 2 squared.
Yeah, it doesn't matter if you put the 2 or the -2 because it's going to cancel out, but I'll just put the 3 numbers exactly the way they were up above. Okay, so if we do this out, 2 squared is 4, 3 squared is 9, -2 squared is 4. What's 4 plus 9 plus 4? 17. And just like with the distance formula, if you can reduce that, you generally redo. Okay, and the last one is a scalar product. I want to find the length of W, well, not the length of that, I want to triple W. Okay, so what would we get if we triple W? Yep, 9I, -12J, plus 15K. That's it. 9I minus 12J plus 15K. So any questions on the magnitude, scaling, adding or subtracting in 3D? Okay, we're going through it a little quicker because we've already done it all in 2D and it's very, very similar. Okay, so the last thing that we learned how to do in 2D was a dot product. Okay, how do I do a dot product in 2D? Okay, pretend the Z1 and Z2 weren't there. What would be the formula?
Is it x2 multiplied by x1?
Yep, we multiply x1 and x2. So you do that. What else?
And then y1 and y2.
Okay, y1 and y2. What else? And you add them. So now we're just going to extend it one more step. So what's going to be the last calculation in 3D? Add z1 times z2. Okay, so now to do the dot product in 3D, multiply your x's, plus multiply your y's, plus multiply your z's. Okay, so next we'll find a 3D dot product. Okay, and the answer when you do the dot product is going to be what? What kind of thing is it? It's a number. So in this case, we're doing a vector times a vector, and we're getting a number. Okay, keep that in mind. In this case, a dot product gives you a number. Okay, we'll come back to a cross product in a little bit. Okay, so I want to find the dot product between these two vectors. Right, so Adrian, could you give me the first two things I would multiply together to do my dot product?
Two things you multiply would be 2I, 5I.
So what would you get when you do that?
10I.
Yep, so we get 10i. Well, actually just 10.
Oh,
Right? Just 2 times 5 is 10.
all right.
And Curtis, can you give me the next thing?
You would multiply together -3 and 3,
Yep.
and that'd be -9.
Okay, so we get -9. And Sam, what about the last two things?
Multiply -k and 6k, so that would be -6k.
Adrian, what did he do there? He said -6k for the last part.
And the last one,
What-
let's see.
what-
There's no K.
There's no k. Yeah,
It's just 6.
it's just -6. Okay, when you're doing a dot product, the answer is a number. Always a number. So you're just using the numbers. All right, let's see. 10 minus 9 is going to give me 1. And what's 1 minus 6? -5. Okay, so that's our dot product. So what did we use the dot product for in 2D? To find the angle. So what do you think we're going to do next?
Find the angle.
Yeah. So to find the angle between two vectors in 3D, what was the formula in 2D?
Cosine theta of equal.
Equals
Yeah.
dot product
Over the magnitude of V with the magnitude of V.
over the magnitude of u times the magnitude of v. Well, in 3D, it's the same formula. The only difference is that's a 3D dot product, which I just taught you how to do, a 3D magnitude, which we just did on the other page, and a 3D magnitude. Each individual thing is now a 3D, but it doesn't change the formula at all. Okay, so it's the dot product over the product of the magnitudes. So what we'll do is we'll use the two vectors I just had up above. We'll find the angle between them because we already know one thing we need. We already know the dot product.
Wait, the bottom is the dot product from magnitude, right?
The bottom is the product of the magnitudes. So whenever you do a dot product, what has to go in box 1 and what has to go in box 2? What kind of things? No. When you do a dot product, what goes in here and what goes in there? Vectors. Okay? The only thing you can do a dot product with is two vectors, v and w or v1, whatever you want to call them. Okay? The bottom is not a dot product. It's just a regular multiplication. The magnitude of u, that's a length, times another length. Okay? In the bottom, it's numbers. Okay? But at the top, it's a vector dot vector. Okay, okay, so let's find the angle between u and v. Okay, I'm just going to double check, but I think those are the same. 2i, -3, 6, and 5, 3, -1. Yep. Okay, so we already got the dot product. What was the dot product? -5. Now I need the length of u and the length of v. So Ryan, what's going to be the first number that I put under my root to find the magnitude? And what do you have to do with the 2?
Square.
Yep. So we're going to put down 2 squared, which is, yep. So I'm just going to write 4. John, the next number that I'm going to square, and if you can do it out. Yep, negative 3 squared is 9. And Lauren, the last number we're going to square, which is 36. So if you add 4, 9, and 36, what do you get? 49. So what's the length of u? 7. Okay, in this case, we got a nice answer. That doesn't always happen, but it did this time. Okay, Luke, how about the next part? What's going to be the 3 numbers I add to get v?
25
Yep,
plus 9 plus 1.
perfect. So 25, 9, and 1 gives me the square root of 35. If I could reduce it, should I worry about reducing this? Why not? Yeah, I still have to do the inverse cosine. This isn't the final answer to the problem. It's just something I'm going to plug in to get my final answer. So if you have a root and it's not the final answer, don't worry about reducing it. Okay, so cosine theta equals, Alex, what's going to go on the top of the fraction?
Negative 5.
-5. And Hannah, what's going to go on the bottom? Yep. Yeah. 7 square root 35. Now, the answer that I have on the right, that's the cosine of theta. How do I get rid of cosine? Inverse cosine. Okay, so inverse cosine of -5. Okay, you can try it without parentheses, but I'm going to put the denominator in parentheses. So 7 square root 35. So it'll do that part first. And I need a division sign in there somewhere. Right? That should be good. Okay, so the angle between these two vectors is about 96.9 degrees. Okay. So any questions up to that point? Okay, so everything we just did in 3D, that was a good review for all the 2D stuff as well. Okay, so the last thing we're going to look at, this is something new. Okay, the cross product is a different way to multiply 2 vectors. We already have this way. Vector dot vector equals a what? A number. I'm going to show you what vector cross vector is right now. Okay, so the cross product is a different way to multiply 2 vectors. How would you know in the problem whether they want you to do a cross product or a dot product? You will see this symbol for a dot product. You'll see this symbol for a cross product. Okay. As I mentioned earlier, a cross product only applies to 3D. You cannot do what we're doing right now in 2D. It's not possible. And there's a lot of different applications to cross products. We don't look at any applications. All I want you to know is how to do it. Right, so there's a lot of different ways to find the cross product. Okay, I'm going to give you a way that is probably the simplest way to do it. And it uses what's called Sarris's rule. Okay. And Sarris's rule is basically going to involve setting up all our numbers, kind of like this. Anybody remember what it's called when you put all your numbers in an arrangement like that? A Sudoku? We kind of, but not that many numbers. We don't have that many numbers. Yeah, a matrix. Okay? We just put all our numbers in a matrix. All right. So suppose these are our 2 vectors. Okay? Vector v has a x, a y, and a z-axis component, and so does vector w, an x, a y, and a z. If you wanted to write it without the I, J, and K, it would be A1, comma B1, comma C1, with the brackets. Okay, so there's two 3D vectors. Okay, the first step to finding a cross product is you're going to create a 3 by 3 matrix. That means 3 rows by 3 columns. Exactly what I just drew up above. Okay. In the 3 by 3 matrix, okay, row 1 is going to be exactly what I wrote right here. And that's the same in every problem. You just put an I, a J, and a K. Okay. In row 2, you're going to write the 3 numbers that were in front of I, J, and K in the first vector. Okay, so A1, B1, and C1 will all be numbers. And then in the last row, you're going to put down A2, B2, and C2. Okay, I'm not really going to explain why this works. All you have to understand is how to do it. Okay, so that's the first step. Okay, any questions on how we set up that 3 by 3 matrix? IJK, first row. The coefficients of your first vector, coefficients of your second vector. Right, so the next step. You're going to copy columns 1 and 2. You're going to take these 2 columns, and I want you to put a copy of them right where I just circled. Okay? Right next to it. So what's going to happen is your first row is going to be I, J, K, and then you're going to put down, ignore the colors, I'll explain what those are after. All I want you to do is put down I, J, K, and then copy the first 2 to the end, IJ. Okay, I've circled some diagonals, but you don't need to know what those are right now. You're copying these 2 rows, and you're going to copy them to the end. So like you're going to put this column, you're going to put a copy right here. This column, I want you to put a copy right there. Okay, so then you're going to have A1, B1, C1. That's what you already have. Copy A and B to the end. Okay, and then the last thing, you have A2, B2, C2. I want you to copy A and B to the end. Okay, again, when we do it, all of these are going to be numbers. All I did was I took these 2
And you just put them to the end?
and I just copied them to the end.
Okay, okay.
So the I and J got copied to the end, the A and B got copied to the end, and the A and B got copied to the end. Yep. When I refer to columns 1 and 2, that's column 1, that's column 2. Copy them to the end. Okay, so as far as setting up the problem to be able to solve it, that's it. That's all. That's what you have to set up. Now we have to use that to solve it. Okay, and the calculation you have to do, it's just multiplication and addition, but you have to do it the way I'm showing you. First thing you want to do is take, and I used colors to try to make it clearer, take everything that's on red 1 and multiply it together. Take everything that's on red 2 And you're going to put plus the product of everything that's on red 2. And then you're going to put plus the product of everything that's on red 3. So when you're done this step, you're going to have something I, something j, and something k. Okay. So take all the red diagonals, you multiply them each separately, and add them up. Now, the blue diagonals, we're going to do pretty much the same thing, except you're going to multiply them, but you're not going to add them. You're going to subtract them. So you're going to multiply everything that's on blue 1 and subtract it. You're going to multiply everything that's on blue 2 and subtract it. And we're going to multiply everything that's on blue 3 and subtract it. Okay, so when we do it with actual numbers, it's going to be a lot less letters. Okay, and I can actually show you how it works. Red 1. Gold 2. Okay, if you don't have different colors, what you could do on your paper is you could call them diagonals 1, 2, 3, 4, 5, 6. You could do it that way if you don't have different colors. Okay, does everybody at least have the formula written down? Not if you understand how to do it, because I'm going to do that right now, but you at least have it. Yes? Okay, I really think once you see it with numbers, it's not like a trig identity like kind of level problem. It's pretty straightforward multiplication and addition. You just got to see it with some numbers. All right, so here's our 2 vectors I want to find the cross product of. V is 2, 3, 5. That's all you really need. And W is 1, 2, 3. Okay. What goes in the, you don't have to put the extra columns yet. Just tell me the top row. IJK. Okay. What's row 2? 2, 3, 5. And what's row 3? 1, 2, 3. 1, 2, 3. Okay. What's the next thing I have to do? Take the first 2 columns and copy them to the end. Okay. So we have IJ, 2, 3, 1, 2. Okay, now all you have to do is multiply the diagonals, but you got to remember which ones you add and which ones you subtract. The ones that go down and to the right, you subtract. Okay, so I'll circle them in red just like I did on the other page. Let's try red. There's 1, 2, 3. Okay.
So you combine like terms to get one new vector?
We are going to combine like terms, yep. What do you get when you multiply I times 3 times 3? 9i. What about j times 5 times 1? 5j. And k times 2 times 2? 4k. Okay. And now, go back to the other page for a second. You're going to multiply the other 3 diagonals you didn't do yet. You'll know if you mess up on the diagonal, because if your diagonal only has 2 things in it, you circled it wrong. The diagonals should all have 3 things. Okay, so that one, and that one. And what am I going to do with each one of those? We're going to subtract them. What's 1 times 3 times k? So I'm going to subtract what you just said. 2 times 5 times I. And you're going to subtract it. And 3 times 2 times j. Okay, so now we're going to look. What's 9i minus 10i? Negative I. What's 5j minus 6j? Negative j. And what's 4k? Take away 3k. Plus k. What kind of answer is that? That's a vector. So I just answered this question. When you do a cross product, the answer is a vector. It's a vector. Any questions on that? There's really not a lot of work to write down. That's all the work for the problem. Okay, so that's V cross W. Does anybody remember what I said if you switch the order? I mentioned it quickly yesterday. It's going to be the last one we finish up with. But does anybody remember what I said? I said it was going to come out different. So let's switch the order and finish up with that and see what it comes out to. And I think after you see what it comes out to one time, you'll never have to go through it again. Because if you do it one way, and you've done this before, you should already know what happens when you switch it. Okay, but you'll know after you do it one time. Okay, what's going to go in the first row? Nope, not W. I. Yep. And what's going to go in row 2?
1, 2, 3.
Yep. So now the 1, 2, 3 is going to be here. And the last row? 2, 3, 5. Okay, so put your first 3. What do I do after that? Copy the first 2 columns. IJ, 1, 2, 2, 3. And we can circle them both. I mean, we don't need to. We're going to multiply all the diagonals that go down and to the right. Somehow you got to remember down and to the right are the ones you add. Okay? So what's I times 2 times 5? 10i. What's j times 3 times 2? 6j. And what's k times 1 times 3? 3k. And now we're going to subtract. Minus 4k. Minus 9i. Minus 5j. What's 10i minus 9i? I. 6j, take away 5j. J. And 3k minus 4k. Negative k. Okay. Compare that answer to the one that we just got. The sign switch. So in terms of sketching it, what does that mean? What happens when you switch all the signs? What happens to the vector? The direction. Changes direction. How about magnitude? It's nothing. So in other words, if I ask you to find a cross product 2 ways to switch it, all you have to do is take the first way, make everything a negative, or change the sign, and you get the second way. Okay? That's a cross product. Okay. So, any questions on the cross product? All right. Okay, so your packet I gave you, I don't think it has any cross product problems because that was section 5.7. They do a lot of stuff with the cross product. I just made one up for you to copy down. Okay, so page 363, that's in the packet. 15, 17, 29 to 35 odd, 41, 43, and 51. And then I want you to try this cross product problem. I'm asking you to do V cross W and W cross V, but am I really asking for two different things? Or is it hard to find the other one? Not if you get the first one. Okay? Page 363 is in the packet. The problem below it right here is not. So you got to copy that down. Okay, it'll also be in the review video. The other thing is I will be after school tomorrow for extra help. And just as a reminder, if you're doing skills, the test has to be done by the 31st. Okay, so you got tomorrow after school, anytime during the day tomorrow, next week anytime during the day, or next week after school on Thursday.